Hello friends, welcome to our channel, Gajpal A Learning. In today's video we will continue the topics of acid-base titration, that are strengths of acid-base, pH of solution, common ion effect, acid-base indicators and the theories of acid-base indicators. So let's start the video. First is strengths of acid. In the context of acids and bases, strength refers to the degree to which an acid can donate a proton, H, or a base can accept a proton in a chemical reaction. The strength of an acid or a base is crucial in determining the extent to which an acid-base reaction will occur. There are two main types of strengths: acid strength and base strength. First, acid strength. The acid strength of a compound depends on its ability to donate a proton. The stronger the acid, the more readily it donates a proton. There are a few factors that influence acid strength. A. Atomic structure. The acidity of an element increases across a period, left to right, in the periodic table and decreases down a group. This is due to factors like increased electronegativity and smaller atomic size, which affect the stability of the conjugate base formed after proton donation. B. Electron withdrawing groups. Compounds with electronegative substituents, such as halogens or nitro groups, enhance acidity by stabilizing the negative charge on the conjugate base. C. Resonance. Molecules with resonance structures that can distribute negative charge over multiple atoms tend to have greater acidity because the negative charge is dispersed, making the anion more stable. D. Strength of the conjugate base. Strong acids have weak conjugate bases, meaning that the resulting anion is stable. This results in a more favorable acid-base equilibrium. Examples of strong acids include hydrochloric acid, HCl, sulfuric acid, H2SO4, and nitric acid, HNO3, while examples of weak acids include acetic acid, CH3COOH, and carbonic acid, H2CO3. Second, base strength. The base strength of a compound depends on its ability to accept a proton. Stronger bases are more likely to accept protons. Factors influencing base strength include: A. Lone pair availability. Compounds with readily available lone pairs of electrons are more likely to act as strong bases. B. Atomic size. Larger atoms and ions tend to be more basic. As you move down a group in the periodic table, the atomic size increases, and the ability to donate lone pairs for proton acceptance improves. C. Electron density. Elements with higher electron density, such as oxygen and nitrogen, can readily donate lone pairs, enhancing their basicity. D. Resonance and electron withdrawing groups. Similar to acids, the presence of resonance structures or electron withdrawing groups can affect the basicity of a compound. Examples of strong bases include hydroxide ion, OH, alkoxides, RO, and amides, NH2. While examples of weak bases include water, H2O, and ammonia, NH3. Understanding acid and base strengths is essential for predicting reaction outcomes, designing chemical reactions, and explaining the behavior of various compounds in different contexts. Next is pH of the solution. The pH of a solution is a measure of its acidity or basicity and is defined as the negative logarithm, base 10, of the concentration of hydrogen ions, H+, in the solution. It quantifies the concentration of these ions, which are responsible for the characteristic properties of acidic solutions. The pH scale ranges from 0 to 14, with 7 being neutral. A pH below 7 indicates acidity, while a pH above 7 indicates basicity. Mathematically, the pH is expressed as pH equals minus log H+, where H+ represents the concentration of hydrogen ions in moles per liter, mole per liter, of the solution. Key points about pH. A. Acidity and basicity. A lower pH value indicates a higher concentration of hydrogen ions and thus greater acidity. A higher pH value indicates a lower concentration of hydrogen ions and greater basicity. Neutral solutions have a pH of 7, indicating equal concentrations of hydrogen ions and hydroxide ions, OH-. B. Logarithmic scale. The pH scale is logarithmic, meaning that each unit change in pH represents a tenfold change in the concentration of hydrogen ions. For example, a solution with a pH of 3 has 10 times more hydrogen ions than a solution with a pH of 4. C. pOH. The pOH is the negative logarithm of the concentration of hydroxide ions, OH-, in the solution. It's related to pH through the equation pOH equals 14 minus pH. In neutral solutions, pH and pOH are both 7. D. Buffer solutions. Solutions with pH values close to 7 are often referred to as buffer solutions. These solutions resist drastic changes in pH when small amounts of acids or bases are added. A. Indicators and pH meters. The pH of a solution can be determined using indicators, substances that change color depending on the pH of the solution. Additionally, pH meters provide precise measurements of the pH value by measuring the electrical potential difference between a pH-sensitive electrode and a reference electrode. F. Environmental and biological significance. The pH of a solution is critical in various contexts, including industrial processes, environmental monitoring, and biological systems. Living organisms and their cellular processes are highly sensitive to changes in pH, and maintaining a proper pH balance is essential for their survival and proper functioning. G. Effects on chemical reactions. The pH of a solution affects the rates and outcomes of chemical reactions, as many reactions are pH dependent. For example, the behavior of enzymes, which are essential in biological processes, is strongly influenced by pH. In summary, pH is a fundamental concept in chemistry that quantifies the acidity or basicity of a solution by measuring the concentration of hydrogen ions. Understanding pH is crucial for a wide range of applications, from chemistry labs to environmental monitoring and biological research. Next is common ion effect. The common ion effect is a phenomenon in chemistry that describes how the presence of an ion in a solution can affect the solubility or ionization of a slightly soluble salt or a weak electrolyte. It occurs when a solution already contains one of the ions that is produced by the dissolution or ionization of a compound. This additional ion, referred to as the common ion, has an impact on the equilibrium position of the reaction, leading to a decrease in the solubility of a salt or a shift in the ionization of a weak acid or base. The common ion effect can be explained using Le Chatelier's principle, which states that a system at equilibrium will respond to changes by shifting its equilibrium position in a way that counteracts the change. Solubility equilibrium and the common ion effect. Consider the dissolution of a slightly soluble salt like silver chloride, AgCl, in water. AgCl, solid, rightwards harpoon over leftwards harpoon Ag plus, aqueous, plus Cl minus, aqueous. If a solution already contains a soluble salt that provides one of the ions in the equilibrium, for example, adding sodium chloride, NaCl, to a solution containing AgCl, the common ion effect comes into play. The Cl- ions from the added NaCl will push the equilibrium to the left, decreasing the dissociation of AgCl and consequently reducing its solubility. Ionization of weak acids and bases and the common ion effect. The common ion effect also influences the ionization of weak acids and bases. For instance, consider the ionization of acetic acid. CH3COOH rightwards harpoon over leftwards harpoon CH3COO minus plus H plus. If sodium acetate, CH3COONA, is added to the solution, it introduces the CH3COO- ions. According to Le Chatelier's principle, this will suppress the ionization of acetic acid, leading to a decrease in the concentration of H+ ions. Applications of the common ion effect. The common ion effect has practical applications in various fields. First, buffer solutions. Buffer solutions are prepared using a weak acid and its conjugate base or a weak base and its conjugate acid. The common ion effect helps maintain a relatively constant pH in these solutions when acids or bases are added. Second, control of precipitation. The common ion effect can be used to control the precipitation of certain salts. By introducing a common ion into a solution, you can decrease the solubility of a salt and encourage its precipitation. Third, analytical chemistry. The common ion effect is employed in quantitative analysis methods, such as titrations, to influence the direction of reactions and accurately determine concentrations. In summary, the common ion effect demonstrates how the presence of an ion in a solution affects the equilibrium of reactions involving that ion. It's a fundamental concept with applications in various chemical processes and analytical techniques. Next, buffer solution. A buffer solution is a special type of solution that has the ability to resist changes in its pH when small amounts of an acid or a base are added. In other words, buffer solutions help maintain the stability of their pH values despite the addition of acidic or basic substances. Buffer solutions are widely used in various applications where maintaining a stable pH is crucial, such as in biological systems, chemical reactions, and laboratory experiments. Buffers are typically composed of a weak acid and its conjugate base, or a weak base and its conjugate acid. This pairing allows the buffer solution to effectively neutralize added acids or bases without leading to drastic changes in pH. The ability of a buffer to resist changes in pH arises from the principles of equilibrium and Le Chatelier's principle. Let's know how buffers actually work. When an acid is added to a buffer solution, it reacts with the conjugate base present in the solution. This reaction consumes the added H+ ions, preventing a significant decrease in pH. Similarly, when a base is added, it reacts with the weak acid component of the buffer, removing H+ ions and preventing a sharp increase in pH. Now, components of a buffer solution. A. Weak acid. The weak acid component of the buffer donates H+ ions, helping to counteract the effect of added bases. Common weak acids used in buffers include acetic acid, CH3COOH, and carbonic acid, H2CO3. B. Conjugate base. The conjugate base component of the buffer can accept H+ ions, helping to counteract the effect of added acids. For example, the conjugate base of acetic acid is acetate ion, CH3COO-. C. Buffer capacity. The ability of a buffer solution to resist pH changes depends on its buffer capacity. A higher buffer capacity means the solution can absorb more acid or base without a significant change in pH. Buffer capacity is maximized when the concentrations of the weak acid and its conjugate base are approximately equal. D. pH range of effectiveness. The pH range in which a buffer is effective depends on the dissociation constants, Ka and Kb, of the weak acid and its conjugate base. A buffer works best when the pH of the solution is close to the pKa, negative logarithm of the Ka, of the weak acid. This is because at the pKa, the concentrations of the weak acid and its conjugate base are equal, providing maximum buffering capacity. Applications of buffers. First, biological systems. Buffers play a crucial role in maintaining the pH stability of bodily fluids like blood, which is essential for normal physiological functioning. Second, laboratory work. Buffers are used in various laboratory experiments to ensure that reaction conditions remain constant and pH-sensitive reactions are not disrupted. Third, chemical reactions. Buffers are employed in chemical reactions where maintaining a specific pH is vital for reaction rates and product yields. In summary, buffer solutions are essential tools in chemistry and biology for maintaining stable pH levels. They work by utilizing the equilibrium properties of weak acids and their conjugate bases to resist changes in pH caused by the addition of acidic or basic substances. Next is acid-base indicators. Acid-base indicators are substances used to visually determine the pH of a solution by changing color in response to changes in hydrogen ion concentration, H+, or acidity. They are particularly useful for qualitative assessments of pH, allowing individuals to identify whether a solution is acidic, neutral, or basic based on the color change observed. Indicators are commonly used in various applications, including titrations, educational demonstrations, and quality control. Theories of acid-base indicators. There are two main theories that explain how acid-base indicators work, the Bronsted-Lowry theory and the Lewis theory. First, Bronsted-Lowry theory of indicators. According to the Bronsted-Lowry theory, an acid is a substance that donates a proton, H+, and a base is a substance that accepts a proton. In the context of indicators, the indicator molecule itself undergoes a proton transfer, leading to a change in its color. Example, consider the indicator phenolphthalein, which is colorless in acidic solutions and pink in basic solutions. In acidic conditions, phenolphthalein exists in its protonated form, HIN+, and is colorless. In basic conditions, it accepts a proton to form its deprotonated form, in-, which is pink. HIN+, colorless, rightwards harpoon over leftwards harpoon in-, pink+. H+. The color change occurs at a specific pH called the indicator's pH transition point, which corresponds to the equilibrium between the protonated and deprotonated forms. In the case of phenolphthalein, this pH transition point is around pH 8.2. Second, Lewis theory of indicators. According to the Lewis theory, an acid is a substance that can accept an electron pair, and a base is a substance that can donate an electron pair. In terms of indicators, the color change is associated with the ability of the indicator molecule to accept or donate an electron pair during the interaction with H+ ions or hydroxide ions, O-. Example: methyl orange is an indicator that is red in acidic solutions and yellow in basic solutions. In acidic conditions, the indicator molecule donates an electron pair to a proton, forming a covalent bond and resulting in a red color. In basic conditions, it accepts an electron pair from a hydroxide ion, leading to a different resonance structure and causing a yellow color. The Lewis theory provides a more comprehensive explanation for indicators because it considers electron pair interactions beyond just proton transfer. Some of the indicators are: first, phenolphthalein. Color change, colorless to pink. pH range, transition from pH 8.2 to 10.0, colorless in acidic solutions, pink in basic solutions. Second, methyl orange. Color change, red to yellow. pH range, transition from pH 3.1 to 4.4, red in acidic solutions, yellow in basic solutions. Third, bromidimol blue. Color change, yellow to blue. pH range, transition from pH 6.0 to 7.6, yellow in acidic solutions, blue in basic solutions. Fourth, litmus. Color change, red to blue. pH range, transition around pH 7, red in acidic solutions, blue in basic solutions. Fifth, phenol red. Color change, yellow to red. pH range, transition from pH 6.8 to 8.4, yellow in acidic solutions, red in basic solutions. Sixth, universal indicator. Color change, various colors across the pH scale. pH range, provides a spectrum of colors at different pH values, allowing for more precise pH determination. Seventh, thymol blue. Color change, red to yellow. pH range, transition from pH 1.2 to 2.8, red in acidic solutions, yellow in basic solutions. Eighth, cresol red. Color change, red to yellow. pH range, transition from pH 7.2 to 8.8, red in acidic solutions, yellow in basic solutions. Ninth, alizarin yellow R. Color change, yellow to red. pH range, transition from pH 10.1 to 12.0, yellow in acidic solutions, red in basic solutions. 10th, neutral red. Color change, red to yellow. pH range, transition from pH 6.8 to 8.0, red in acidic solutions, yellow in basic solutions. In summary, acid-base indicators work by undergoing structural changes that result in a color change in response to changes in pH. The Bronsted-Lowry theory explains the color changes in terms of proton transfer, while the Lewis theory provides a broader perspective by considering electron pair interactions. Both theories contribute to our understanding of how indicators serve as pH indicators in various applications. Thanks for watching this video.